But it was very
Yeah. I got it.
It's really good.
Okay, on clock here is a slightly fast. But I think it's from towards the start. Ready. So it's a pleasure to be here again. Professor Chen at Princeton University. We will continue lectures on capabilities.
Oh, okay, thank you. So, I mean, this is my last lecture. So I'll talk about the separativeness and the properties of the modular, and if time permits, I will talk a little about the local KCP theory. So this is, let's recall, this is the theorem I mentioned in my yesterday's lecture. So as I tried to explain to you yesterday that a stack admits a separate good modular space is a very strong properties of the stack. So you can think about the stack is a global quotient stack that like has very strong consequence on the orbital geometry of this quotient. For instance, you can conclude that for each orbit, if you take the closure, there is a unique minimal orbit contained in the closure, and unique minimal closed orbit contained in the closure, and also the inertial group is reductive. So how do we prove this? let me first introduce some very nice criterion by Harper, Leisler, and Henlos. So they give some like a functorial criterion, evaluative criterion to check when a stack has a good modular space. So let's say R is the DVR. And we consider the stack theta R, which is just the A1 R quotient by GM. So the GM is GMR, maybe up here. So you have basically have this like a family of spec R. And in this direction, you have a GM action. And you have a limiting point here. So we say X is theta reductive. I think one annoyance is in Harper's book and in their paper, the terminology is slightly different. I think, but I just follow the terminology in their paper. I think one of them they call theta reductive later becomes theta companies, and then I will introduce S companies. Later they call it S reductive. So anyway, I just follow their paper's notion. So this is reductive if. So if you look at this stack, there's one point which is 0. So K the relative field, and this is the gerb or module GM. So you see about this action, the 0 is the fixed point, the unique fixed close point. And if that the theta take on this point, map to your stack, can be uniquely extend to this movie. So, I mean, the uniqueness often is very easy. I mean, that's usually if you have a fine diagonal, this is always the case. The thing is that there exists such a movie. This is called theta reductive, and a similar criterion called S companies. So here we consider ST, which is equal to spec R add the two element ST module. So let's say the DVR is R pi, pi is the uniformizer, and then ST is equal to pi. And this guy, again, module a GM action, such that the S, like mu S and T, mu inverse T. So the weight cancel each other. So if you draw a picture, I mean, again, it's just like this is ST, and R is like this kind of curve. So this is called STR. Again, I mean, it's kind of equivalent surface with a GM action. And again, there is a unique point which is given by 0 ST 0 0, which is a gerb. And so then you can imagine that the criterion I need is this map to X. And be uniquely lift to this. So this is called S. This is called S complete. That's called the theta reduct. S complete. That's called the theta reductive. And the main theorem they show, maybe I write here. Upper Leisler Hellos. They show that X. I mean, let's say finite type. R in stack X Let me emphasize this result is only true for characteristic 0. So over K with characteristic 0. Admits separated modular space if and only if X is theta reductive and S complete. So let's give you a if and only if evaluative criterion to check your stack admits a good modular space. So no, that's what I'm saying. It's over K, K0. Yeah. So let me try to explain this. I mean, when you first say this, it looks a little bit abstract, but let me try to unwrap this notion a little bit by using our example. And you say how this could, what this mean. But let me just say that what we really prove is that this stack is theta reductive and S complete. So, well, yes, we did. So then, of course, we can just apply their criteria. Let me just focus on this one. I think this is more tricky, and it's actually also more interesting. So let's try to digest what this means. So we have this guy mapped to X. Now we want to say this can be extended to X. That just means if I have a semi-stable Fano, so if I have a family of K semi-stable Fano variety over this guy, then I can extend it to a K semi-stable Fano variety over a family of K semi-stable Fano variety over this. That's exactly what this extension means. Right? This is a stack. So I have a map to a stack, just means I have a family. So that just means the family over here can be extended to a family over STR. So that's what I need to prove. So but what's STR take out 0? If you take a look at this, this is precisely just the double. This is just precisely the double curve. So you basically have a spec R, green spec R with spec K. The K is the generic point. I mean, since if you take the S is not equal to 0, then the action becomes free. Then you get one spec R. And again, when you take T not equal to 0, then you get another spec R. And then you glue them together, you got this guy. So in other words, I have a family over this double point curve. So what does this mean? So you have a family of Fano. This data is precisely just say I have an X over spec R. And I have X prime over spec R. Such a both will give me a family of K semi-stable Fano varieties, such that the XK is isomorphic to X prime K. Right. So basically I start with this kind of data, and then I want to show I can extend this family. And if you look at this family a little bit more, you realize that if you look at this, that point, maybe let me draw you some color. So this point corresponds to this GM, and this point corresponds to this GM. And let's just say that you can actually extend the family over this point. So So basically, let's just say that I want to find the common degeneration of both x and x0 pi, such that the common degeneration is still k-semi-stable. So that's exactly one of the corollary I wrote down. That basically this is equivalent to that information, but as long as I can make it to the family. So okay. Then how do I construct this family? I mean, anyway, this limit of algebra was constructed by Luhmann and myself in an earlier paper, but we really have to work quite a bit to somehow find out the construction. But once you have this kind of perspective, you realize that the only possible extension over this guy is fixed. The information is fixed. You just have to work out that information to show it's k-semi-stable. So what could be possibility of this point? So let me see if I have x over st then so far I don't know there is such one. But if there is one, then this f lower star minus mkx. So that will be the f0 minus mkx0. So this is a vector bundle on this surface, take out a point. So then, of course, the total vector bundle will be just this guy. So this is the inclusion J. So if this guy exists, it has to be this one, right? So now we have this information. So what we need to show, we need to put all this JF lower star MKX0 together. And if we can show this, if this is finite generated, then we can take approach. So that tell me the only possible extension of this as some polarized scheme is just given by taking approach of this one. So that the only possible extension is already there. You just have to show this finite generation, and then you can proceed to show that the approach of the central fiber is indeed a k-semi-stable Fano variety. So the main, I mean, once you have this perspective, the main point is there is no construction anywhere. The algebra is fixed. You just have to show it's finite generated and then show the central fiber is k-semi-stable. Once you can do that, you are done. So, I mean, I'm not going to explain too much about the finite generation part. I mean, but I just want to say that. Let me just give one remark about the finite generation, and then I'll move to properties. So finite generation follows from the fact that if I look at the filtration induced by vanishing order of x0. So sorry, I should give a, let me call this H. H lower star minus mkx direct sum of OL. So this is a finite generated R algebra. And then I have some like I look at the vanishing order. X0 centered on the central fiber. I look at the vanishing order. Then I want to say this filtration is fine generated. So once you have that, you can you can either say that's essentially equivalent to the fine generation of this one. And so you just have to show fine generation that. And this is implied by the fact that there exists a delta linear equivalent to lambda minus kx such that 0 lambda less than 1, such that the log discrepancy of a x0 plus delta of x0 prime is less than 1 between 0. So okay, I mean this pair is low canonic. Then you apply PCHN. So somehow you just find basically this x0 prime can be. I mean, this guy lambda actually can choose to be arbitrarily close to 1. So it's something like again like a LC place of some complement, but you wiggle the coefficient a little bit. So this gives you the fine generation, and then you continue to prove the central fiber is k-semi-stable. So somehow the fine generation coming from here, and it's their step. I need that. It's their step. I need both x0 and x0 prime are k-semi-stable. I mean, you can start this filtration for adding to a family with integral fibers, but in general, there's no reason it's fine generated. But in this setting, it's fine generated because here I use the XX0 are k-semi-stable. So I mean, again, this is maybe like I have a two fiber, I have a two central fiber, and it breaks some kind of two-way game. Okay, so this is everything I want to say about the existence of good moduli. So another part I want to say is so this is the first proof, but I want to discuss some like a new proof in that this is Popa to prove the good moduli space itself is compact. So how do we prove this? So let's say if I have an x0 over a puncture disk, such that this is a family of k-semi-stable. A family. So what I can do is I can complete this family, maybe after some like base change, after some final base change of the base, such that I have this fiber, and but the central fiber of this family is KLT Fano. But after all, I don't know it's k-semi-stable. I mean, MMP can give you a KLT Fano limit. That's like a MMP type result. But where the semi-stability comes from, that's completely unclear, right? So then we want to, so if X prime is unstable, so it's not k-semi-stable, then we want to find the new family X prime, again, after base change, after base change, such that, of course, over the central fiber, so over the generic fiber, this is still my original family. So, but now I change my central fiber such that the delta x0 prime is strictly less than delta x0. So somehow if I want to say that if my central fiber is unstable, but my but my general fiber is semi-stable, then I can actually increase the stability of the central fiber, and then we know such delta x0 can only take finite many values in the range of let's say delta. So the thing I start with and 1, maybe let's say I would say minimal of this and 1. So if I get 1, then I'm done. I'm k-stable case. So basically, let's just say there are only 5 possible values I can take. Next time is just from the boundedness. So from boundedness, because my volume, the volume is fixed. Now I look at the delta larger than this number, then I know it's a bounded family. Then I know delta is a constructor function, so there are only 5 many values you can take. So the option is, how do I make this strict inequality work? So originally, let me just say this in words. When we look at the first proof of the Popaness, we use something called a theta stratification theory by Harper-Leisler. So the offshoot of Harper-Leisler's theory is that if you look at the total stack of all final varieties, so if I can provide a kind of functional on this stack, or even on the one parameter family of this map to this of object in this stack, such that each unstable object there is a unique optimal discretization. Then roughly say we got a theta stratification, and that theta stratification will imply you can increase this stability function each time by using that function. Give the theta stratification, and then after final steps you get a stable object and stable feeling. However, the slightly annoying thing is delta itself is not coming from theta stratification, because yesterday I mentioned usually the divided compute delta is not unique. You might have a phase of divided compute delta, phase of valuation compute delta. But the theta stratification theory really need a unique one. So we have to modify this delta by some like a second function. And then we cook up an alphabetical order of 2 values. And then we try to minimize that function. So it's a little bit technical, but to me, the main, the thing I really feel a little bit unsatisfied is that even you assume everything works in this Harper-Leisler theory, we got such functional. It's not clear to me what the X0 prime is. I mean, if you look at Harper-Leisler's original argument, it comes from some like a general result about stack. So we really want to find a bilateral geometry description of what's a replacement, and now we do have one. So let me state our theorem. So the more technical version of that theorem is the following. Is that if I have an X mapped to C the curve, such as this is a puncture curve, such as this is a family of final variety. And I make the assumption that the delta of the central fiber is smaller than the delta of the genetic fiber and possibly 1. So I make this assumption. So that means so for instance, if the general fiber is K-semi-stable, then this really just means the central fiber is not K-semi-stable. And then there exists a relative delta function. I will define this on X and E centered over 0, computing delta with the property such that first, I mean, you have this X mapped to C. You can extract this E over this X on some partial model, and then you run MMP to other direction to get a new model X prime, such that the X0 prime is basically just E. So essentially just do this tool again. You extract one divider over the central fiber, and then you construct another. And this is still a family of KOT final variety. So this is the first part of my statement. And then the second statement is exactly what we need, that the delta X0 now is strictly less than delta X0 prime. So I have this increasing of the stability function. So that's basically this proof really realize this new replacement by some divider which comes from some like a relative function, which I'm going to define it. So delta C, I mean, it's actually just very similar to the delta X. Now X is a family. This is just defined to be informer of AX. So the log discrepancy of X, but now have a parameter C is the number X0 E. And so this is just discrepancy of E with respect to this pair. And the S is just given by, now I have this FE filtration on the family. I restrict this filtration to the central fiber of X0. And I look at all possible E. So this depends on C. And for our purpose, to make that theorem work, we need 0C, strictly less than 1. So this is going to be the C we choose. And then, so once you have this, you can just play all the games which I discussed in my first second lecture, that you show that this informer is given by, so basically we show informer is computed by some E. And furthermore, and satisfy so maybe let's say this is step A, satisfy the condition 1 in the theorem. So basically, you really say how this kind of find or this business of really find a divider which calculates this informer comes into the proof of Popanese. I mean, the original proof we use the absolute version. Here we just basically modify the proof to make it to work in the relative version, and then that will give me E. So we need that E to compute this function, and that E exists is actually you need all this stuff I discussed in my first 2 lectures. So, but this is essentially very kind of similar to what we know in the absolute case, that we can find a divisor which computes the minimum. Then the second part is to prove that the strictly increasing. And this boils down to several inequality. So the first is one can show that the delta x0, so the delta of the central fiber, is actually the same as if I choose C to be x. So if I choose C to be 0, then this is the same. This flows from some kind of inversion of a junction. So this basically kind of inversion of a junction type result. Not very hard to prove. And then, of course, by definition, this is less or equal to AXX0E defined by SFE. Well, I mean, because this is infemoral, so it's equal or less or equal to this one. But the E is centered on the central fiber. So then there is a strict inequality that for C positive, this is less than 1 minus X0 E, and the same as here. Because this number is just larger than this number, because E is centered on this fiber, so there is some positive contribution from here. But from our definition, from this factor E computes this. This E is equal to delta CX. This is equal to that's just the choice of E. So far, nothing happened. But the really new stuff is we show that this is less than delta x0 prime. So this is the new part. And this inequality actually doesn't follow from any general theory. Only until we work it out, we believe this is true. I mean the first part is this part essentially follow from the same kind of philosophy from in the actual case, but the second part is kind of new. So if you put all of them together, you got a certain inequality here. But the main subtlety is actually to prove this inequality. And okay, I don't have time to discuss more details about the proof. I'm happy to discuss it if you are interested. So I mean, in my last 30 minutes or so, I want to discuss a little bit about the local case stability theory. I mean, you already see this from Princeton's lecture. I mean, the thing about normalized volume, that's what I want to discuss. So if I have an X, if I have such a K or T singularity, and so I mean, since this is singularity, local germ, I can just assume X is spec R. And well, now I consider the valuation, which is centered under this point. So in other words, the valuative ideal is always like MX primary. And this is a space for any element here, any valuation which is centered at this point, I can define two invariants. The first is the volume of V. And this was first defined by Lawrence I, Laderfeld, and Smith. So this is just given by the limit of the length of R more AK and the K power to n factorial. So here AK is precisely the function, or the function with at least a K. So because this is a center at this point, this is going to be a primary ideal. So this length is a finite number, and then you can define it. This is K go to infinity. I mean, why don't you put is the dimension of this, of course. And also you can define the law of discrepancy, which I already used it in any case. And Chile's definition is that I define the volume of evaluations is given by the AXV power to N volume V. So, I mean, this is the main definition, but it could happen that this guy is zero. But one can show that when this guy is zero, this guy is actually infinity. So in that case, we always assume it's infinity. So this is AXV equal to infinity, and this is AXV. So basically, we just determine that the infinity times zero is still infinity. So basically, this number, and this is the full valuation, and we define a volume of a singularity, a chaotic singularity, just to be the, again, to be the infimum of all such V. So then this will be a natural invariant attached to any chaotic singularities. So the first question is, of course, you ask whether it's trivial. I mean, Chile, in his paper defining this invariant, he showed that this infimum is always positive. So it's actually a non-trivial invariant. And then he asked a bunch of conjectures, which later are all proved. So let me mention some basic properties of this. So the first is Bloom 17 and myself 19. So we show that this function, this volume function, always, so Bloom showed it always has a minimizer. But actually, I show that it's also always a cost monomial minimizer. Again, the valuation is not some random one. It has to be cost monomial. So the next thing, which was first proved by Mihnea and Chen, and later there's a proof by Bloom, Liu, and Chi, I think maybe 24, is that this minimizer, the minimizer is unique up to rescaling. One can easily check that volume V is equal to volume of lambda V. So in other words, again, this function is defined on a slice of the valuation of the rescaling. And let's show that except the rescaling, the minimizer is unique. And then the last thing we show is that this, so if I call this minimizer V, again, this associated gradient ring of this R is finite generated. So just to finish the conceptual picture, we actually already showed at the beginning, if we assume all of this is true, and then if I look at I call this guy X0, so maybe spec of this guy is called X0. So the gradient ring, I just make a spec is X0. It has a power section. And this power section actually has a canonic co-weight, which is given by this V. So this V together, this is something called K semi-stable final cone. So in other words, you can roughly think that any chaotic similarity has a canonical way degenerate to some K semi-stable object. But here, this is not a final variety. This is a cone. So, you know, usually we talk about cone. If it's a sixth action on cone, then the base will be a final variety. Then the K semi-stability of this cone is the same as the K semi-stability of the base. But that's only for the case when the action is C star. So now I just have a more general action with some kind of co-weighted real. So it's not necessarily C star action, but we can still define K semi-stability. Again, I'm not going to talk too much about this. I mean, if you are interested, we can discuss this later. I want to talk about some applications of this, but I want to first draw some corollary from this properties. So, for instance, this will immediately imply that if I have a singularity, if I have a KLT singularity, if I look at the local fundamental group, actually I look at the local fundamental group of the smooth of the regular part, so which is often could be larger than the fundamental group. Just take out this point. So this I call local fundamental group. This is smaller or equal to n power to n divided by the volume of x. So why? I mean, first we know this is finite. And then you can take this finite universal cover. And then we have this guy, this uniqueness will imply that, so okay, maybe let me just say that if y map to y map to x, so this is quasi-eta. This is quasi-eta. Then the the volume of y in y is the same as the volume of x times the degree of this f. So this kind of degree of type formula will immediately imply this result, because the universal cover, the volume is at the most n power to n, which is the volume of the smooth point. And you know that the degree they differ is at the most by this number. So that's the size of the upper bound of the local fundamental group of this. So, but to have this, this basically is the consequence of the uniqueness. So let me just say that we have this kind of properties. So, okay. So now I want to talk about the recent work. I mean, not that recent, maybe last year by Han, Qi, and Chen. So let me see, how do I say? Okay, let me first say that if x is projective, if x is a projective variety, and let's say L is a big Lie bundle, big and Q Lie bundle, big divisor on x. So I define alpha xx. So this is the alpha invariant. It's just the infimum of local threshold of xd, such as all d, like a Q linear equivalent to L. So basically, all the Q divisor in L, you look at the LCT. So there are two fact, okay, I mean, one inequality involved this local volume was already mentioned by Christine. So I will just talk about another one, which is actually simpler than the one Christine talked about. So I'll just say that a lemma for adding x, now under this assumption, for adding x in x, the volume of x in x. So for adding point, the local volume is at least the volume of L times alpha x L to n. So I'll give a proof of this. This is really easy to prove. So, but let me just first assuming this lemma. So now, for now, let me just assume this lemma. Now I consider X the general type variety. I consider X general type. And I run any sequence of minimal program. So we know by BCHM that if we run MMP with scaling, this is always going to terminate. But we actually don't know if we run any MMP, this is terminate or not. But I mean, this we still don't know. I mean, it's done from their paper. But what I say that if this is an MMP sequence, I know that the volume of Kx is the same as the volume of Kx prime. You know, because MMP doesn't change the volume. And one can usually see that the alpha Kx is actually smaller than alpha x prime Kx prime. Because, you know, MMP essentially just make this Kx to be more and more positive in some sense. So then because of this, you immediately conclude that for any x prime in x prime, the local volume of this is larger than some fixed constant. This constant only depends on x, which is basically just the volume of Kx times alpha Kx power to n. Right? I mean, the answer here is this number. This number does not depend on x prime. So it doesn't depend on how you run MMP. It only depends on the x you initiate with. So then, if you combine this fact with this fact, you conclude that the local fundamental group is uniformly bounded. So particularly, for instance, the Cartesian index is uniformly bounded. Because, of course, the Cartesian index is the most of the local fundamental group. So basically, this implies that the Cartesian index of any integral weight divider, for instance, Kx prime, this is bounded. This is bounded. Actually, we just use. I mean, up to now, we use the fact that that inequality, which comes from the uniqueness. I mean, this is not trivial result. I mean, that need a proof, but we can actually apply something stronger. So there. Teacher and I prove the following thing, that if I look at a fixed dimension, if I fixed dimension, I look at so I prove maybe two things. The real stuff is in this side, that if I fix dimension, I look at the volume of all xx, dimension x is equal to n. So I look at all possible such kind of set. And then the only accumulation point of this set is 0. So once you fix a positive number, you look at all positive number above it, it's always discrete. There are only 5 mapping out there. So we are another result we need to is that for this application, that we need basically if you look at the volume, you look at the singularity, which is larger than some constant positive number. So I fix the V0 larger than 0. So after all, I want to conclude that I want to say their singularities are bounded if you fix the lower bound of the volume. That's not correct on the nose. We actually know that this is the x-axis itself might not be bounded, but this kind of object is bounded. So it's bounded, it's a degeneration to some bounded family by some like torus action. So this will imply lots of boundaries of the singularity of this. So for instance, this will, for us, this will imply that the MLD is bounded from above of all such kind of singularity. So then, we have the volume has a lower bound here. So the Cartesian index is bounded. That means the MLD could only be in a discrete set. And also it's bounded from above. So, the only possible MLD is really just a finite many of them. Of course, if we want to apply Shortcroft's conjecture, Shortcroft's way to prove termination of flips, you need another side, you need another conjecture, which is called the lower semi-continuity conjecture, which actually I'm not sure it's true or not. But at least you can, originally Shortcroft needed two conjectures together to imply termination of flips. But under this setting, I think one conjecture can be completely replaced by this kind of argument. The ACC of MLD is not needed, at least in the general types, type setting. And I really hope that one can extend this argument to non-general type case, and then we don't need to have ACC of MLD anywhere. It's an interesting question, but maybe it's not needed anymore. So then I want to show you the proof of the lemma. I just want to show you that everything is simple. But you have to assume all these facts about the KLT singularities, which are hard to prove. But I want to show you this lemma. The proof of this lemma is not. So basically, I want to show that for any V, AX V n times the volume of V is larger than the alpha n times the volume, right, of the L. So then, because this is for any V, if I take infinitely, that's still true. I mean, again, this number, then you can rescale it. So we may assume AXV is just equal to 1. I just rescale this such that AXV is equal to 1. And if I look at the AK, the relative ideal, which is precisely the F, VF is larger than K, then I look at the exact sequence of tensor M. Okay, let me just make sure my number are correct. This is AM divided by alpha, the V, map to L tensor M, map to L tensor M, O module, that's AM divided by alpha. So we have this, but because alpha, because AXV is equal to 1, we know that H0 LM tensor AM alpha V is equal to 0. Since otherwise, if you have a section, that means I have a section, vanishing order along V is at least 1 over alpha. So that will imply the local threshold is actually less than alpha. So that's contradictory to our assumption. So we know this is 0. The alpha is the alpha invariant. Then this will imply I have the injection of H0M injects to H0 L tensor M tensor O M alpha. Well, of course, this side is the primary ideal. So the H0 is just the length of this guy. This will just, you divide by the same thing. That precisely imply that the volume of L is less than the volume of V divided by alpha power 2n. So that's a proof. So you know, I mean, there's really not too many deep stuff. But actually, I mean, in the paper of Han, Chi, Zhuang, they actually prove something deeper than this. They use this result, this kind of boundary result. They show that if you look at all this, any sequence of this MMP, if you look at the fiber of all the flipping and flipped locus, they all belong to a bounded family. So that still doesn't conclude everything is bounded, but that's the strongest result which I can draw. But here we have to assume general type. Okay, let me stop here. Thank you.
So, can you say maybe, like, if I had just a little bit more of a global picture, like, so if I had like X delta or something, to what extent was the local picture somehow able to capture the like global picture?
I don't know what you exactly mean. I mean,
So I had a germ, like actually the germ of a kale piecing there, but
this is certainly one local global combined inequality. And I mean, yesterday, Princeton mentioned another inequality is volume X is larger than minus Kx times m plus 1. But this is only for Fano. Yeah, I think this is right.
so I mean, so for your applications in mind, you're thinking L is minus K or minus K plus delta. Or...
Oh yeah, there are tons of applications of this. I mean, for instance, when they started the three-dimensional, the K module of three-dimensional Fano varieties or two-dimensional, I mean, that's even simpler. But in the three-dimensional case, they look at the volume. I mean, okay, maybe I can mention this a little bit. If you look at the dimension x is equal to 3, the largest volume is 27. That's just smooth point. And actually, the next one is the rational double point is 16. And the next one is 22/2. Actually, they decrease quite fast. We know we prove it's discrete, but the optimization theory have a pretty good picture. I think Yu and Liu classify this up to something like 9, maybe, or 8, or 5, some number like this. So within this range, you basically know every singularity. So if you plug in this, they'll just say you basically understand pretty well of the singularity appear on K semi-stable Fano variety of the volume, something like the P3 divided by 3. So that's like 20 something. So, if you work like for K moduli of Fano variety with volume larger than this range, then you have a pretty good understanding of what local singularity could be. I think this is very useful for people to study explicit Fano K moduli for 3 folds. Unfortunately, for dimension larger than 3, we know very little. For instance, we conjecture the second largest volume will be always given by the rational double point. I mean, there's great progress working towards this question by Chili and his collaborator Miao, but so far it's still open. But this, for instance, implies that what Christian mentioned, the cubic K moduli would be the same as the GIT moduli. Yeah, so I think if you know the local picture pretty well, I mean, people have already understand that this will be very useful to study Fano K moduli, at least when volume is large. But I think I would say the application by those people are somewhat unexpected, and I hope there will be more applications toward the original MMP type questions.
Place X by a singular higher dimensional subvariety, something like that, like would there be purpose of
I mean, you can study normalized volume of a generic point of a subvariety. And one can prove that that's the same as the volume of a general point on that subvariety up to some like a dimensional constant. But I mean, that proof is non-trivial, but I think by now one can prove it. I think we wrote it as a conjecture somewhere, but now I think it follows from what we know.
You ask the same question again. So this kind of geometry moduli is good and helpful for analysis in the sense of Yau's integral estimate. Then from this conclusion, we could out uniform kind of C0 estimate. Yeah, I don't know. I'm actually, yeah, I don't know whether it's really useful for analysis or not. Yeah, I mean, I hope it's useful, and actually, yeah, I don't care it that much. But yeah, I don't know. Yeah.
Chenyang will still be here for a week. Middle is one o'clock, which has confidence. Thank you.
Thank you.
Before we announcement that tomorrow we're going to be stairs. So room number 505. So we are not using here. And also, yeah, so for those people who are going to attend the conference next week, then you are encouraged to re-register tomorrow afternoon this week. So, by doing so, that we have a better estimate of the institution will be, this week. Okay, so tomorrow we'll split.
For this, I know, from the job, the business, I have to get the.
Yeah.
Whereas I, works and that works. No, I mean, that's another, say I have someone from Hamas. So for them, they're different, they're very hard. So those kids, that's then that. Probably only getting over to Canada.
This is a better stuff here. It's about like. So, like, much less space. But what I mean by example of something like, for example. Exactly, anything on the boundary. So we just. Anything we might.
So make sure you don't have.
And capability.